Okay, in this video we're going to look at testing a claim about a proportion with Statcrunch. So here are the directions, and before we start this, since it's a proportion, we need to always check two things. Well, for Triola, we need to check that NP is greater than or equal to 5 and NQ is greater than or equal to 5. And for Sullivan, they ask you to do this one. And that's because we want to have be able to use a normal distribution here on our hypothesis test. Otherwise, we have to go back to a binomial if this fails. And I will do one of these later where it fails and we have to do a binomial. But the first one just shows the more common where this is in fact true and passes. So n is 200 times 0.1 is our p, 20, and then 0.9 times 200. Of course, they both pass, so we can use this method. Down below under Sullivan, NPQ, right? 1 minus p is just a q, so 0.9 is q, 0.1 is p, kind of going backwards, times 200. Passes. So we can use the normal method to test this claim. Okay? So the first thing is to read this. They have a p-value approach they want us to do. Here's the information. They want us to use the tables, but let's use Statcrunch first, and then I'll show you the table. So go down here, stat, we're under proportion stats, because this is a proportion. We have one sample with summary. The number of successes are your x value, 30. Observations are your n value. And then remember, the initial hypothesis is always an equal to for these. So you should always have equal to. It's not even an option to change it. 0.1. And then we have a greater than. So we're looking at a right tail test here. Greater than. And click compute. We will get our p-value and our z statistic. So we don't have to do any type of work there, and we just look at the p-value and make the claim according to the level of significance. It is less than the level of significance, right? So it's outside that boundary. So we're going to reject the null hypothesis because the p-value is less than alpha. If it was greater than alpha, we wouldn't reject. Okay, now I'm going to show you just this table here because that's how they use to find the p-value. But we need to use the formula that's in the book for the z statistic. And I kind of did the work out here for us. So this is the formula for a z statistic. We have the sample proportion minus the population proportion divided by the square root of these values here. The proportions, p and q multiplied divided by n. So I filled them in, 30 over 200 minus 0.1, and then let's put it in the calculator. I thought you might want to watch that, how I did it. I'm going to do 30 divided by 200 and keep it in the calculator and not round off. Hit enter. It doesn't need to be rounded. Minus 0.1. Enter. Then divided by, I'll put this all in one big parenthesis and see if we can get it under the square root. So parenthesis to get the numerator in, that's a 0.1 times 0.9, right? P times Q. End of my parenthesis. Luckily the square root's still going, divided by 200. And then that's everything I need. 2.357022, 2.357, round the 5 up to a 6. Whoops, I must have wrote that wrong there, huh? Round the 5 up to a 6. So 2.36 for 2 decimal places. Now, to find the p-value, it is a right-tailed test. So we're looking for this here, and we go to the chart, 2.36. I go to 2.36. Right about right there to 0.9909 or 0.991, right? If we round up, so 0.991. So 1 minus 0.991. Or if you even did what they had in there, 1 minus 0.9909, then you would just round it to 0.0091. Same kind of thing, p-value. Because we're looking for the right side, it's a right tail test, so the p-value would be to greater than, so we want that 1 minus the probability that the z-statistic gives us. If it was a left tail test, then we'd get a negative z-value most, and then we'd be looking to the left of that, and the table always gives the left. Okay, here's a new example, and this example is where we fail to reach this requirement, and we have to use a binomial calculator. We can't use a normal approximation on this stuff. So 2 professors at a local college developed a new teaching curriculum designed to increase the students' grades in math classes. In a typical developmental math course, 48% of the students complete the course with a letter grade of A, B, or C. The experimental course, 18 of the students enrolled, 12 completed the course with an A, B, or C. Is the experimental course effective at the 0.05 level of significance? Okay, so first off, we need to check these values. I haven't checked the NP, but we can see that this fails. Let's try the NP for Triola, and then we'll do Sullivan. NP, so P is 48%, 0.48 times N is 18, and we fail. We already failed one, we don't need to do the other. So now we can go down to here, N again is 18. See, we're talking in such a small sample size, times 0.48. times Q, 0.52, and we fail. So we cannot use the normal approximation z statistic for this. We're going to have to use a binomial. So we'll set up the hypothesis though. Again, it's a proportion, so you want to choose P, right? And there's the population proportion, 48%, so equal to 48. It's always equal to. The alternative hypothesis is that they're making a math course so that more than 48%. They want it to be better, right? So they want to make it so that more students pass the class. So we want to have a greater than sign. So this is a right-tailed test. We've already verified that this fails. Now it's a binomial experiment, and this is a little more why. There's a fixed number of trials, right? With 2 mutually exclusive outcomes. The trials are independent and the probability of success is fixed at 0.48 per trial. Determine the p-value. This is a Statcrunch problem, calculator in binomial. So we're doing back to binomial. We have the number of students of 18, not very many. We have the 0.48 for our probability. And now what do we need to calculate? We need to calculate to the right, right? We're looking, it says, of the 18 students enrolled, 12 completed the course with a letter grade. So if 12, 13, 14, 15, 16, 17, 18, going to the right, we want to be greater than. So let's go to the right of 12 or more. And then we'll get our p-value. So the right portion is considered here the p-value to the right of 12 students completing the course. Now we compare this 0.088 with our level of significance, 0.05. Is the p-value less than that? If it is, we reject the null hypothesis. The p-value is not less than that, so we do not reject the null hypothesis, right? Says no, do not reject the null hypothesis because the p-value is greater than alpha. There is insufficient evidence to conclude that the experimental course is effective. Alright, if you continue down in this problem, if you were doing this problem, you'd see that they kind of do a problem. They increase the number of students here to 54, 36 complete. So now that you get your numbers above 10, you're able to do a z-statistic, which is just easily done in a proportion. Proportion stats, one sample with summary. The number of successes was 36 out of the 54. And now we're doing 0.48. And we're still going to be doing that greater than, compute. Our z statistic now changed to 2.75. Our p-value is much smaller, 0.003, and we're able to easily calculate it here. Now is the p-value less than alpha? And it is, so we reject the null hypothesis. There is sufficient evidence to conclude it is effective. So it's kind of interesting that with a small class we weren't able to see the data clearly. Getting larger numbers allows us to go and make a normal approximation of this data, right? And then we can see that it is effective. So the key here is having more n. Always have more people for your sample to make your conclusions.